goal of this lab was to examine and understand the motion of a spring mass system in which the mass swings in an arc while also oscillating on the spring. We did this by using the physics principles and created a model to compare the motions. The physics principles used were Newton's second law, Hooke's law, and the energy principle. The results were that we were able to create a model that accurately predicted the motion of the spring and discovered the relaxed length of the spring to be 0.103 meters and the spring constant to be 6.597 newtons per meter. For this problem, we were given the mass of the weight and the length of the spring. Using Tracker, we were able to find the initial position of the spring. The length of the spring was used to calibrate Tracker, and the position data gained from the video was put into a CSV file. To find Ks, we first had to find the period. The period was found by taking the length of time between 3 oscillations and dividing that by the number of oscillations. The period was found to be 1.551 seconds. Then we put the period and the given mass into this equation to find the spring stiffness, which turned out to be 6.597 newtons per meter. Using our spring stiffness, we were able to find the relaxed length of the spring. We did this by setting the force of gravity equal to the force of the spring and then rearranging the equation until we got the relaxed length of the spring. Our spring constant and relaxed length were then added to the Python code. L was used to describe the length and orientation of the spring, while S describes the stretch or compression of the spring. For this system, the change in energy is equal to the change in kinetic energy plus the change in potential energy of the spring plus gravitational potential energy. Because nothing in the surroundings is transferring energy into the system, work is 0 and thus delta E is 0. The gravitational, kinetic, and spring potential energies were found using the equations above and put into the code. In this system, F net was the sum of the force of the spring and the force of the gravity. The force of gravity was found by multiplying the gravitational constant by the mass and the y direction, while the spring force was found using Hooke's law, which multiplies the negative spring constant by the stretch or compressions of the spring. These were entered into the code, and the resulting net force was used in Newton's second law to predict the updated velocity in ball v, which was then used to update the position of the ball. The blue arrow is the spring force, the black arrow is the force of gravity, and the blue dot is the predicted motion of the mass. The red dot is the actual motion of the mass. As you can see, the blue dot and the red dot follow each other fairly closely, but get farther apart as time goes on. Some possible errors could be from not accurately clicking the center of the mass, or be caused by drag. In the graph, the green line is gravitational potential, the red line is spring potential, and the blue is kinetic energy. As you can see, all of the lines add up to the yellow line, which represents delta E. Because there is no change in E, there is no work being done on the system, which means that the energy principle is satisfied and delta E remains 0. What does it mean? Question 2. Using the data you obtained in Tracker, make 2 separate estimates for oscillation periods. First, estimating the period of oscillation from the position data, and second, by estimating the period of oscillation from the Y data. Compare the 2 estimates and discuss. As you can see, the X oscillation period is slightly longer than the Y one. This is because X and Y components follow 2 different patterns of motion. The X component follows a pendulum pattern of motion, while the Y component follows a spring pattern. These 2 motions have completely different ways of calculating the time periods, and thus will rarely be the same.